On April 10, 2026, for astronauts aboard NASA's Orion capsule, Artemis II re-entered Earth's atmosphere returning from a lunar flyby. Surface temperatures on the heat shield reached approximately 2,760 degrees Celsius. That is hotter than molten steel. There is no backup system for the heat shield. It either works, or the crew does not survive. This video explains exactly how heat shields work, what they are made of, why the engineering is so difficult, and why Artemis II's shield became one of the most debated pieces of hardware in NASA's recent history. Reentry is a speed problem first. The International Space Station orbits at roughly 7.7 kilometers per second. That is 27,700 kilometers per hour. When a capsule deorbits, it carries all of that kinetic energy into the atmosphere. Air cannot get out of the way fast enough. It compresses in front of the vehicle. Compression generates heat, not friction, as is commonly believed. The shockwave itself is the heat source. Peak heating occurs between 60 and 80 kilometers altitude, where air density is just high enough to compress but still thin enough for the vehicle to be moving fast. Surface temperatures during reentry depend on vehicle shape and entry angle. Apollo capsule peak reached approximately 2,760 degrees Celsius at the heat shield face. Space Shuttle leading edges was up to 1,650 degrees Celsius. For reference, iron melts at 1,538 degrees Celsius. Aluminum melts at 660 degrees Celsius. The thermal protection system must keep the underlying structure, usually aluminum or carbon fiber composite, below about 177 degrees Celsius. That is a 1,500 degree temperature gap the material must bridge. The shape of the vehicle matters as much as the material. A blunt body, a rounded, wide nose, creates a detached bow shockwave. The hot plasma forms several centimeters in front of the surface, not on it. That gap is the first line of thermal defense. A pointed nose would attach the shockwave directly to the surface. Temperatures would be catastrophic. Julian Allen at NACA proposed the blunt body concept in 1951. Every crewed re-entry vehicle since Mercury, Apollo, Soyuz, Dragon uses this geometry. Thermal protection systems fall into two categories. Ablative shields sacrifice material deliberately. The outer layer chars, melts, and vaporizes. That phase change process absorbs enormous amounts of heat and carries it away from the surface. One use only. Reusable systems insulate without burning away. The material absorbs very little heat and conducts it slowly enough that the structure stays cool. Multiple uses, but more complex to maintain. Both strategies solve the same problem with opposite approaches. The right choice depends on mission requirements, entry speed, vehicle mass budget, and whether reuse is planned. An ablative heat shield has 4 zones during peak heating. Char zone, outermost layer, already burned. Provides some insulation. Pyrolysis zone, material is decomposing. Gases are being driven off. Virgin material, intact ablator below, not yet affected. Bond line, the interface with the spacecraft structure. Must stay below design temperature. The pyrolysis gases are critical. They bleed outward through the char and cool the surface by transpiration, essentially sweating heat away. This is called blockage effect. Remove any one of these layers, and the system fails. AVCOAT is the ablator that carried Apollo astronauts home from the moon. It is an epoxy novolac resin filled with silica microballoons and fibers, packed by hand into a fiberglass honeycomb matrix bonded to the capsule's aluminum structure. Each honeycomb cell was injected individually, about 370,000 cells per heat shield. Apollo re-entry velocity from the moon was approximately 11 kilometers per second, faster than a return from low Earth orbit. The shield lost about 3 centimeters of thickness during re-entry. That ablation is intentional. It means the system is working. NASA revived AVCOAT for the Orion capsule. The formulation was slightly updated, and that update had consequences. After Artemis I in 2022, post-flight inspection found chunks of char had broken off in over 100 locations. The root cause, the reformulated AVCOAT had lower permeability. Pyrolysis gases could not vent outward normally. Pressure built beneath the char layer and blew pieces free. For Artemis II, NASA did not redesign the shield. Engineers modified the reentry trajectory instead, a steeper, more direct descent that avoids the pressure conditions behind the Artemis I damage. Some experts accepted that fix. Others publicly did not. PICA, phenolic impregnated carbon ablator, was developed by NASA Ames Research Center in the 1990s. Carbon fiber preform is infiltrated with phenolic resin. During heating, the phenolic pyrolyzes, releasing gases. The carbon fiber structure remains as a low-density insulating char. PICA has a very low thermal conductivity. It is also extremely lightweight. The Stardust mission used PICA in 2006. Reentry velocity was 12.9 km per second, the fastest atmospheric entry of a human-made object at that time. The heat shield survived. SpaceX adopted PICA-X, a modified version, for the Dragon capsule. It performs comparably at lower production cost. The Space Shuttle used a different philosophy entirely: don't burn away the material, insulate with it. The primary tiles, called HRSI, high-temperature reusable surface insulation, are made from silica fibers, 93% empty space by volume. Density, about 144 kilograms per cubic meter. For comparison, water is 1,000 kilograms per cubic meter. The silica is an extremely poor thermal conductor. Heat absorbed on the outer surface travels slowly through the tile. By the time re-entry is over, the heat has not yet reached the bond with the aluminum frame. The tiles can be held by hand on one side while the other side glows at 1260 degrees Celsius. That demonstration was used in shuttle-era training. The shuttle tile system had a known weakness: tiles were brittle and bonded individually. Approximately 20,000 tiles covered the orbiter. No two tiles were the same shape. Replacement required precise custom-cut pieces. On STS-107, Columbia, a piece of foam insulation from the external tank struck the leading edge of the left wing during ascent. The impact damaged the reinforced carbon-carbon panels, a different, even higher temperature material used at the wing leading edges. On re-entry February 1, 2003, hot plasma entered the breach. The wing failed. The orbiter broke apart. The root cause was not material failure. It was a maintenance and inspection process that normalized anomalous foam strikes. Reinforced carbon-carbon is used where temperatures exceed what silica tiles can handle. On the shuttle, RCC covered the nose cap and wing leading edges, the highest heat zones, reaching 1650 degrees Celsius or above. RCC is a carbon fiber composite with a carbon matrix. Both reinforcement and matrix are carbon. The material is then coated with silicon carbide to resist oxidation. Bare carbon burns in air at high temperatures. The thick layer prevents that. RCC is strong, lightweight, and handles extreme temperatures, but it is brittle and expensive to manufacture. A single shuttle nose cap costs several $1 million. Orion uses a variant called carbon-carbon composite for its forward bay cover. SpaceX took an unusual approach with Starship: stainless steel structure, ceramic tile TPS. Stainless steel can withstand higher temperatures than aluminum before structural failure, roughly 870 degrees Celsius versus 177 degrees Celsius. That gives more margin before the tiles need to stop all the heat. The tiles are hexagonal, approximately 15 centimeters across, made from a silica-based ceramic similar to shuttle HRSI but manufactured differently. Gaps between tiles are intentional, they allow thermal expansion without cracking. Tile attachment uses a fibrous matte interface layer. Tiles are bonded with ceramic adhesive. Replacement requires removing the bonded tile and rebonding a new one. Early test flights showed tile losses. SpaceX redesigned the attachment system iteratively. A fundamentally different approach: deploy a large surface area before re-entry begins. NASA's lofted low Earth orbit flight test of an inflatable decelerator demonstrated this in November 2022. A flexible inflatable toroid, a donut shape, inflates around the vehicle before atmospheric entry. The large diameter creates more aerodynamic drag at higher altitudes, where air density is lower and heating is less intense. The benefit: peak heating is reduced because the vehicle slows down earlier, before reaching the dense lower atmosphere. The flexible aeroshell packs compactly for launch. It can scale to larger diameters than rigid heat shields, which are constrained by rocket fairing size. Mars missions with heavy payloads would benefit significantly from this approach. Heat shield materials are tested on Earth before any flight. Arc jet facilities use electric arcs to ionize gas and produce plasma streams at temperatures and pressures that simulate re-entry. NASA Ames Interaction Heating Facility can sustain plasma at over 8,000 degrees Celsius. Test samples are mounted in the stream and monitored for surface recession, char depth, and bond line temperature. Hypersonic wind tunnels simulate pressure and flow, but typically cannot match the chemical environment of real re-entry plasma. No ground test perfectly replicates flight conditions. Some behaviors, like how pyrolysis gases interact with the plasma boundary layer, can only be measured by flying. Re-entry physics apply beyond Earth. Mars has an atmosphere roughly 1% as dense as Earth's. Entry velocities for Mars missions are similar, but peak heating is lower. However, Mars landers must decelerate from orbital speed to near zero, all in a thin atmosphere. The heat shield must work, and then a parachute must deploy while still supersonic, and then rockets must fire. Perseverance's heat shield was 4.5 m in diameter, the largest ever flown to Mars. Venus has a dense, sulfuric acid atmosphere. Entry heating is severe. The Soviets landed multiple Venera probes successfully in the 1970s and 1980s using thick steel pressure vessels, not lightweight ablators. Returning from the Moon requires roughly 11 km per second re-entry. Returning from Mars, up to 12 to 14 km/s. Higher velocity means higher heating rates, longer exposure, and deeper ablation. HEAT Heat Shield for Extreme Entry Environment Technology is NASA's current development program for high-energy return missions. It uses a 3D woven carbon fiber preform with two layers, a recession-resistant outer layer and a low-conductivity inner layer. Mass savings over PICA are estimated at 40% for deep space entry conditions. No crewed vehicle has yet flown a Mars return entry profile. The engineering is largely extrapolated from unmanned test data and computational models. Modern heat shield design relies heavily on computational simulation. Computational fluid dynamics (CFD) models the shockwave, plasma composition, and heat flux distribution across the vehicle surface. The governing equations include thermochemical non-equilibrium. The air chemistry does not have time to reach equilibrium at these speeds, so standard gas laws do not apply. Ablation models track material recession, gas injection into the boundary layer, and char formation simultaneously. NASA's DPLR and LoRa codes are the primary re-entry CFD tools. Validation requires arc jet and flight test data. Computational models can be wrong. Columbia's wing breach was not in the pre-mission CFD model because no one asked that specific question. Mass is the defining constraint in spacecraft design. Every kilogram of heat shield reduces the kilogram budget for science instruments, fuel, or life support. This is not a minor trade-off. Launch to orbit costs approximately $2,000 to $10,000 per kilogram depending on the vehicle. Apollo's heat shield weighed approximately 850 kilograms, about 14% of the total command module mass. The engineering objective is not the best thermal protection. It is the minimum mass that survives. Ablation depth is designed to be just sufficient, with margin. A thicker shield adds mass for zero benefit. Materials research targets lower density, higher performance ablators to hold the same protection at less mass. Reusability changes the heat shield equation. A single-use ablative shield works for one mission. A fully reusable vehicle, Starship, future point-to-point transport, needs TPS that survives dozens or hundreds of reentries. The shuttle achieved roughly 100 reentries across the fleet's lifetime. Starship targets that per vehicle. Tile replacement after each flight adds cost and turnaround time. The long-term objective is TPS that requires minimal post-flight servicing, inspect, verify, fly again. No current material fully achieves that. PICA X degrades and must be inspected. Starship tiles chip and must be replaced. The performance gap between where the materials are and where the mission requires them to be is still significant. For recent milestones define where the field stands today. Artemis I, December 2022. Orion's AVCOAT shield survived lunar return velocity, but post-flight inspection found unexpected char loss in over 100 locations. Not a mission failure. A design warning. Artemis II, April 2026. First crewed Orion reentry at lunar return velocity. Modified trajectory designed to avoid the permeability-driven char loss seen on Artemis I. The crew: Reed Wiseman, Christina Koch, Victor Glover, Jeremy Hansen. This is the real-world test of NASA's fix. Lofted, November 2022. First successful large-scale inflatable TPS flight test from low Earth orbit. Starship IFT-4, June 2024. First controlled full-scale Starship reentry. Tile losses occurred but were manageable. Belly flop profile validated. For failure modes, define heat shield risk. Burn-through ablation exceeds design depth before reentry ends. Structure is exposed. Tile or panel loss, physical separation of TPS material during ascent or reentry. Entry angle error, too steep, heating rate exceeds material limits. Too shallow, vehicle skips off the atmosphere and does not return. Manufacturing defect, voids, delaminations, or improper bonding in the TPS layer. Columbia was tile loss combined with a damaged material type, RCC, that had no repair capability on orbit. Current crewed vehicles have on-orbit inspection procedures. Orion's heat shield is photographed before re-entry. Dragon is inspected robotically after docking. 6 things to take away. 1. Re-entry heat comes from shockwave compression, not friction. 2. Blunt body geometry creates a standoff shockwave essential for survival. 3. Ablative materials protect by sacrificing themselves, controlled burning. 4. Reusable tile systems insulate through extremely low thermal conductivity. 5. Mass is always the constraint, minimum protection that survives, not maximum. 6. No universal solution exists. Every mission profile demands a different TPS choice. The challenge of re-entry has been solved well enough to land humans on the Moon 6 times and return them safely. It has not been solved to the point where it is routine or cheap. That covers spacecraft heat shields, from blunt body physics to ablation chemistry to inflatable aeroshells. If this was useful, subscribe. The channel covers science and technology. Leave a comment. Which future mission's heat shield challenge do you think is the hardest? Mars direct return, Venus entry, or Starship reusability?